Hello everybody, welcome back to this channel. Today we're going to talk about the waveform symmetries. Last lecture we talked about the Fourier series. The essential thing was to find the Fourier coefficients, including a sub 0, the DC component, and all the Fourier coefficients for the AC components. And if we know the Fourier, the waveform symmetry properties, and we may not need to find all of the Fourier coefficients because some of them are zeros. And today we're going to look at into these properties. As always, I'm going to put the Google Colab notes for this lecture in the description down below. If you have any comments, feel free to leave. And so we're going to look at three different types of the waveform symmetries. The first two are even symmetry and odd symmetry. And these are almost similar to the even functions and odd functions you learned in a long time before, right? And the third type of waveform symmetry, the half waveform symmetry, we're going to take a look at what these properties will entail in terms of the Fourier coefficients. Let's start with the even symmetry. And we see the waveform have ft has even symmetry if the ft is the even function. Of course, here we're talking about the periodic function as well. So ft is going to be equal f negative t. So that means the function is symmetric across the vertical axis, right? If you plot the ft. And let's see what the properties this will have. We know the Fourier series for ft, that's going to be equal a0 plus the sum of an cosine n omega t, and omega the fundamental frequency plus b sub n times sine n omega t. And that's for ft. And if we substitute this replace t by negative t, then we have a0 plus the sum of a sub n and cosine function is even function, right? So therefore the negative n omega t is going to be still going to be equal n omega t, and for sine function, sine is an odd function, so therefore we can pull this negative sign from inside this argument of sine function to the outside of this sine function. So I have sine n omega t, and if you compare these, and I should put brackets in around both, and of course, n goes from 1 to infinity, n goes from 1 to infinity. If we compare these for ft equal f negative t, we would have bn is going to be equal negative bn. That means bn is 0, right? Bn is 0 for all the n's goes from 1 to infinity. Right, so that's the property for the even symmetry. Let's look at an example and see how this will look like in the actual waveform. So here I have a waveform. This is also in the Google Colab notes. And I have a waveform that has a period of 1, right? And this is a pulse function, and this has a duty ratio of 0.8. 80% is non-zero. And the amplitude is 10. So we want to find the Fourier coefficients, and ft features has even symmetry, right? Because this symmetry across the horizontal axis, the vertical axis, even symmetry since based on the plot we can see ft is equal f negative t. And therefore, we only need to find the an, a0, and an's, right? So we need to find a0, and we know the bn is going to be 0. So bn is going to be 0, so we don't really need to find those. And 1, 2, da da da. And we only need to find a0. a0, remember, that's the 1 over t. By the way, we have the t equal to 1. So we're going to have ft dt. You can choose any integration period. We're going to choose from negative 0.5 to 0.5. So and you can just do the area underneath this curve, right? So the period is just 1, and the area underneath the curve 10 times 0.8, that's equal 8. So this is really easy. You can substitute that. You can integrate from negative 0.4 to 0.4 and integrate 10. You get the same answer. And let's look at the Fourier coefficients for the cosine terms, a sub n. A sub n, we know that's a 2 over t, and we choose from negative 0.5 to 0.5, and f of t times the cosine n omega t. And since t is equal to 1, therefore omega is equal to pi over t, that's equal to pi. And so we have 2, since t is equal to 1, so I'm not writing that divided by 1. And I have negative 0.4, because all the from negative 0.5 to negative 0.4, that's 0, so I'm not going to do that. I'm ignoring that interval there, and it goes all the way to 0.4, because after 0.4 to 0.5, that's a 0 again. So during this interval, non-zero interval, here we have f of t equal to 10, and I have a cosine n times omega is equal to pi, right? 2 pi t dt, and we can get this integration. So I move 10 outside, and then I divide this n times 2 pi, and then I can sine n times 2 pi t, and I evaluate the t at negative 0.4 to 0.4. Therefore, I have, let's see, I have a 2 canceled here. I have a 10 over n pi, right? I have sine 0.8. So t equal 0.4, I have a sine 0.8 n pi minus sine negative 0.8 n pi, right? And we know this sign we can move outside, so therefore we can double the answer is quite simple, and I have 20 over n pi times sine 0.8 n pi. So this is the function. This is a Fourier coefficient. We only need a0 and a sub n. So these are the answer for the Fourier coefficient. Let's see if the answer is correct. So what I do is I will go to the Python and we reconstruct the waveform. And so the reconstruction of the waveform, we're going to use the Fourier coefficient we just calculated, right? So we have a0 equal 8, and a sub n is 20 over n pi times sine 0.8 n pi. And we're going to use just those Fourier coefficients to reconstruct the original waveform. So this is the original waveform, and we have so I'm using the step function and also the cosine function to create the original pulse function, and that's the curve in blue. That's the original function that you can see goes from negative 0.5 to 0.5. And here I have exactly 0.4 as the negative 0.4 and to 0.4 for magnitude of 10. And the Fourier coefficients for if n is equal to 0, so this I define the Fourier coefficients here in this function n is the argument. And if n is equal to 0, I have return that to 8, return 8. And if it is non-zero, I have 20 over n pi times sine 0.8 n pi. And I'm going to reconstruct this waveform. So I have x equal a0 plus all the an times cosine n omega t. Omega is 2 pi, right? So I'm just directly writing 2 pi here. And we know this t is 1. So this is a reconstructed waveform. I use the first 50 terms, AC terms, and they did a very good job in matching the original waveform, right? If you have more, if you want to do more, you probably can do even better matching. let's see, maybe 100. Oops, that's 1,000. So let's see if we can run the code. Yeah, so if 100, that's really do matching even closer, right? So we know this Fourier coefficient we did is are correct. Okay, so let's next video clip I'm gonna look at the other symmetry, and see you in a moment.